Hey everyone, and welcome to today's Explainer. I'm absolutely thrilled to guide you through this grade 7 physical science lesson on forces and interactions. Today, we're embarking on what I like to call the engineer's journey. We're going to take concepts that seem, well, totally invisible, the hidden rules that govern how literally everything around us moves, and we're going to learn how to use those rules to solve actual physical problems. It's going to be incredibly illuminating. So let's get right into it.
Okay, let's dive into this. I want you to picture something in your mind for a second. Imagine a massive, fast-moving roller coaster cart speeding down a track, and suddenly it collides right into a stationary bumper at the end of the line. Bam! So what actually happens in that exact split second of impact? Which object pushes harder? What invisible rules dictate how they bounce, stop, or crumple? These aren't just fun questions to think about. They're the absolute core of physical science.
So here's our roadmap for this explainer. We're going to journey from understanding those invisible rules to actively engineering a solution. We'll cover what is a force, then Newton's third law, modeling cart collisions, a common misconception, the toy car design challenge, and we'll wrap it up with a student knowledge check.
All right, Section 1, what is a force?
To understand collisions, we really have to start with the absolute basics. A force is simply a push or a pull exerted on an object. Sounds almost too simple, doesn't it? But don't let that simplicity fool you. These pushes and pulls are the hidden rules governing absolutely all movement and every single impact around us. I mean, you can't build a house without a solid foundation, and you definitely can't understand a roller coaster crash without understanding this basic concept. Whether it's gravity pulling you down, a magnet pulling a piece of metal, or just your hand pushing a door open, every single change in motion starts right here, with a force.
Real quick, before we get too far, here's the essential vocabulary we'll be using to set the stage today. We just defined force. Motion is the change in an object's position. A collision is when two interacting objects crash into each other. A model is a tool we use to represent these interactions, mostly because we can't always crash real roller coasters in a classroom. And finally, Newton's third law, which is for sure the absolute star of today's lesson.
Let's move to and see how this builds into Section 2, Newton's third law. This is it, the golden rule of physical interactions. Newton's third law states that for any pair of interacting objects, the force exerted by the first object on the second is equal in strength, but opposite in direction. I really want to emphasize those two words, equal and opposite. Every single time two objects interact, they're part of this perfect mirrored relationship of pushing or pulling. And this brilliantly illustrates how forces never, ever act alone. They always come in pairs. It's like a cosmic dance. On the left, you see the action force. Let's say that's our roller coaster pushing forward into the bumper. Instantly, and I mean simultaneously, on the right, the reaction force happens. The bumper pushes backward with the exact same strength. Action and reaction, push and push back. Moving right along to Section 3, modeling cart collisions.
So, according to the Next Generation Science Standards, or NGSS, a huge part of physical science is developing models to truly understand these interactions. We need models to describe phenomena that we can't easily measure in real life. To make the invisible visible, we're going to use a number, 50. Let's imagine our fast-moving roller coaster cart hits that bumper with exactly 50 units of force. That's going to be our anchor number for this model.
Now, what's really interesting about this slide is how the table maps out Newton's third law for us. Look at the interacting object on the top row, the roller coaster cart. It exerts 50 units of force in a forward direction. Because of that law of equal and opposite forces we just talked about, the bottom row is basically filled in for us automatically. The bumper literally has to exert exactly 50 units of force, and it has to be in the backward direction. The math is just beautifully balanced.
All right, let's get into Section 4, a common misconception.
As clean as that balanced math is, we need to put on our myth-busting hats for a second, because there's a huge trap here. Notice the text on the left. A very common misconception is that a larger, faster object, like a massive cart, exerts more force on a smaller stationary bumper during a collision. It kind of feels like it makes sense, right? The big, heavy things should push harder. But look at the fact on the right. The actual scientific fact is that the forces between the cart and the bumper are exactly equal and opposite, completely regardless of their mass or speed. The interaction forces are always perfectly paired. Now, the resulting change in motion might be different depending on the mass of the objects, but the invisible force they apply to each other at the exact moment of impact, always exactly the same.
Okay, Section 5, toy car design challenge.
Knowing that these interaction forces are always equal and opposite is incredibly powerful information. And this is exactly where you transition from just being an observer of science to becoming an active engineer. You're going to apply Newton's third law to solve a real problem caused when objects collide. Here's the iterative design process you'll follow. First, you plan a solution to a collision problem. Second, you construct a device for a toy car. Third, you test it out, crash it, to see how well it minimizes or changes motion during the impact. And fourth, you modify your design based on your test results. This continuous loop of testing and modifying is how real engineering happens. So your main engineering goal is to apply scientific principles to design a solution for two colliding objects. Learning isn't just about memorizing facts like equal and opposite. It's about taking that fact and asking, okay, how can I use this to build a safer car bumper? You're actually using these invisible rules to design optimal real-world solutions.
So the crucial point is making sure we have this down before we start building. Let's do Section 6, Student Knowledge Check. Here is your Level A basic check. If your toy car exerts 15 units of force on a wall, how much force does the wall exert on the car? I'm going to pause for just a second so you can think about it. If you said 15 units of force in the opposite direction, you hit the nail on the head. Equal in strength, opposite in direction. Perfect.
Now, let's step it up to level B. This is where we bring the whole shebang together. If the forces are exactly equal, why does a light toy car bounce back further than the heavy wall it crashed into? Think back to what we discussed during our myth-busting section. The answer is mass. While the force exchanged is perfectly equal, the object with less mass, our little toy car, experiences a much greater change in its motion. The heavy wall just has so much mass that the equal force barely affects its motion at all.
You guys have done a fantastic job navigating this lesson today. We've uncovered the hidden rules of equal and opposite forces. We modeled collisions, and we prepared to tackle real engineering problems. So, I want to leave you with this final, provocative thought. How will you use the invisible rules of equal and opposite forces to engineer the world around you? The next time you open a door, drop a ball, or see a car, I want you to see the forces at play, like a giant puzzle waiting to be solved. Thank you so much for joining me on this explainer, and happy engineering!